It's a joint work with Rasmus Pe and Gil Segev, now at the Hebrew University. So I'll go through some of the definitions and the basic results in the field. I hope I'm not repeating too much stuff that was said in previous talks. So what is the set membership problem? We have a universe U, and we just want to build a data structure that answers membership queries over a set of size n. So given a query Q, we have to, the data structure has to output yes if Q belongs to the set and no if it doesn't. It's a very basic problem. And clearly, if you have the entire data structure and you read it and you query all possible queries against this data structure, then you can reconstruct the set itself. So this gives a lower bound on the size of a data structure that would be able to represent such a set. So we have you choose n possible sets of size n. So at least in the worst case, the data structure has to be of size at least log of that, which is roughly n log u, if u is the size of the universe. In practice, it is often the case that this is very, very large. And it could be even absurdly large in practical scenarios. If you want to think of one, think of, say, URLs. Then the set of all possible URLs of length the URL could be a few hundred characters. Then the size of the universe is ridiculously large. And clearly, we don't want to store that many bits for a data structure. So a natural way to sidestep this problem is to look at approximate set membership, where we still, if a member, if the query item Q belongs to the set, we want to answer yes always. But if it does not belong to the set, we allow ourselves a small false positive rate. So we want to answer no only with probability 1 minus epsilon, and epsilon is then our false positive error rate. Now, as we will see, just to get an understanding of why this is interesting, now the size of the data structure could be more or less linear, n times the log 1 over epsilon, where epsilon is our error. So note that the size of the universe has disappeared from this equation, and it's fairly magical. A common scenario is where epsilon is polynomially small in the size of the set, or epsilon is 1 over poly n, and then we have n log n, which is often the case in dictionaries. The error rate could be pushed, often the error rate could be pushed aggressively much higher than polynomially small. And in fact, the regime that we would be interested in is where epsilon is a small constant, but not a tiny one. So I think 1 over 10 is kind of a number to keep in mind. And I will justify it shortly why it is interesting. But you can see that if the set has structure, say for some reason, then clearly we can tolerate a huge error. This is a nice diagram that Rasmus produced. So here the universe is just all these pixels. It's 100 over 100. The set is the circle in the middle. And you can see that the size of the set is roughly 200. And even if we have a lot of false positives, say, so the number of false positives is 4 times the size of the set itself in the right-hand diagram, it's around 10% in the right-hand diagram. It's still very clear what the set is, right? So, but what are the real applications other than finding circles in pictures? Well, these things are extremely common in practice, in databases, in networks, and so on. And typically, the typical scenario is where we have we just want to put a filter in front of some slower piece of memory. So just a canonical example is, say, a web proxy cache. And when a request for a web page comes from a user, we want to determine fast whether this web page is actually sitting in the proxy or whether we have to go to the network and fetch it. So we will put an approximate set membership data structure right here. And the thing to notice is that the cost of a false positive is just a cache miss. So a false positive means that the data structure said, yes, I have this web page, and therefore the client went actually to the web proxy, and the web proxy determined, no, that was a mistake, I don't have it, and then sends the user to the network to fetch it. So the cost of a false positive is not very large. Another thing to notice is that the whole idea is that the filter sits in very fast memory. So these data structures in typical applications sit in real prime real estate. They are really the most expensive, the most fast memory. And therefore, these are exactly the type of data structures where we try to squeeze the bits as much as we can. So a lot of the talk would be around the constant factors in front of the space, or even low order terms. And these things often don't make sense in data structures, but in this case they do. Again, because the way these data structures are being used, it's typically on the most expensive hardware and the most fast hardware that we have. So we want to really use it all the way through. So what are the lower bounds for the static case? So this problem is very old, and in fact, the lower bound was already proved in 78. I'm afraid I don't remember the names of all the authors. The C and the W are Carter and Wegman, and the F is Floyd, but the G and the M I'm missing right now. Gill, the G is Gill, if it helps. So I'm going to prove a different, so I'm going to prove their lower bound, but a different proof, which would just be an introduction to a slightly more sophisticated lower bound that would really follow the footsteps of the lower bound that I show now. So what is the main idea? The main idea is to take this data structure and to use it in order to encode the set S. And by reading, so just like we did previously, we will build an encoding such that if we read the entire encoding, we can reconstruct the set S. And therefore, we will have, again, a bound on the size of the encoding, and therefore on the size of the data structure. And just a note that I'm talking about the worst case space, but it doesn't matter. I could have talked about an average case space because we're talking about entropy here, right? So it's the same inequality for entropy. We can think of the set as being sampled uniformly, and we have the basic inequality that the average size of the encoding is at least the entropy of the distribution which we encode. So there is no real difference between average case and worst case in this technique. So we have the basic fact that the entropy of the set that we encode is log u choose n. And now let's see if we can build an encoding that would imply a meaningful lower bound. So given a set S, we build our data structure, and that data structure has m bits. And now the real step that we have to make is to understand that without loss of generality, we can say that the querying algorithm is deterministic. So we can fix the random. If the querying algorithm has random bits, we just fix them to the best random bits, or even to the average random bits. It would work. And now what this means is that the data structure defines a set of all the yes instances, all the instances for which the data structure outputs yes, it belongs to our set. And our probabilistic guarantee of the data structure implies that the size of this set is at most epsilon times the size of the universe. And now when we have that, all we have to do is to encode our set explicitly relative to the size of this yes instance. So what is the size of the encoding? We have M, which is our data structure. And now we have a perfect encoding. So I want to note here that this is an information theoretic argument. I'm not talking about, I'm not claiming that this encoding is efficiently computable. In particular, this encoding is the perfect encoding, right? We just enumerate all possible sets and we pick the right one. So
your set S is is a subset of those epsilon n things.
Right, right, right. It has to because the data structure has a zero false negative rate.
I see. So you're
right.
using the epsilon false positive. It's more or less the same epsilon relative to the whole universe.
Yes. Yeah, you need to subtract n. You're right. Yeah, I ignore that. Okay. Yes. Yeah, you're right. It should be like, yeah, I'm making it more readable. But it's lower order terms.
You could just modify the definition slightly.
All right. So we have this basic inequality that just follows from the encoding. And now I saved you the Stirling approximation and various manipulations. But if you move things around, you essentially get the lower bound. So you can take easy approximations and get here O of n instead of O of 1. And with really tight work, you can get here O of 1 as well. So this is a really elegant proof. The original proof in the paper is much harder. They give a kind of a combinatorial proof, and this is I don't know what is the origin actually of this proof, but this is a really nice kind of few lines proof, and I think it's a non-trivial fact. Okay, so this is the lower bound. What about upper bounds? So I am sure this data structure had been described. This is a Bloom filter. As you can see, it predates the lower bound, as it should. And this is the first and still most popular implementation for approximate set membership data structures. So in it, we have a bit vector of size m. We sample d functions, and d hash functions, and let's assume that these hash functions are perfectly random and take absolutely no space to store for the sake of this slide. And for an item x, we just use these d hash functions to mark these d locations as 1. And so these d locations are just the d hash functions implied on this item x. And given a query Q, you can answer yes if indeed all these d locations are 1 for this item. And then you can work out what is the, so there are several free variables here. So if I fix an epsilon and the size n, there are still 2 free variables. There is the variable m, and there is the variable d. So you can work out, and it's a nice exercise to work out the optimal setting of these 2 variables given n and epsilon. And you can work out and see that the space is minimized when m is n log 1 over epsilon, which is our lower bound, times log e, which is times 2 point something, right? So, or log e is 1.9. How much is log e?
It's about 1.5.
1.5.
Yeah, square root of 2 times 2.
Right. So, so what can we say about this data structure? It has suboptimal space. Suboptimal space, at least with respect to the lower bound that we've proved, because we have this log e. So as I said, in this particular context, we care about these constants. It supports online insertions. It does not support deletions. It's not clear that deletions really make sense in this context, but still it's a remark. It's not a very good data structure in general to implement, and I will explain why soon. But this is the most common canonical example, to the point where often I think Bloom filters as a term is being confused with the data structure of the problem which it solves. Yeah. Sorry?
What is D?
So D turns out to be, I think, log 1 over epsilon in this case.
And in your lower bound, you didn't use the fact that the queries were small at all. So
At the
if you use the fact that the number of queries is small, can you prove better lower bounds?
What do you mean the number of queries is small?
Like the amount of time it takes to answer the query.
Right. No, I did not use that. In fact, in the upper bound, you can have upper bounds where, at least in the cell probe model, the time is O of 1. So we don't have query space trade-offs. It's just space lower bounds. And so since the query is O of 1, it's kind of a moot issue.
On the lower bound, the question is on the lower bound. Can you prove better lower bounds if you know
So I think you have an upper bound, at least in the cell probe model, not in this particular case. But in other implementations, you will have an upper bound.
Well, my question is, you're saying there's a gap between this upper bound and the lower bound.
In space,
Yes.
right.
But your upper bound has an efficient query time. And the question is there really a gap?
No, so you have a better upper bound both in query time and in space. So a lower bound does not exist.
You haven't shown it yet.
I haven't shown it yet, but you have. This is just.
It's not correct, right? Because he has to ask all these different hash functions just to answer questions. It's a useless data structure. Sorry, that's right.
This is so there are no networking people, so I can be a little bit provocative. But I think this data structure should be a topic of a dissertation on education of science, on meta science, because it kind of it's beyond me how come this particular data structure has become so prominent that everyone knows it. It is implemented all over the place, and there are better alternatives for many, many years. So, sorry?
Hopelessly inefficient.
It appears in some book that is the fundamental book in some course. I don't know. I have no explanation, but it's a compulsory slide. But there are just better upper bounds. So, all right. So here it is. So you can have a dictionary-based upper bound. This is an idea. So in the same paper, it is presented as an idea. It is not completely fleshed out because they did not know how to build these dictionaries. But so what is the idea of a different way of doing it? So you can store the multiset h of s in a dictionary where what is h now? H is just a function from the universe to the range 1 to n over epsilon. And here h could be explicit. It's a universal hash function, so we know that the probability of collision for every particular item, the probability of collision would be exactly 1 over epsilon. And it's a dictionary, so all these signatures are stored and are queried. So clearly, this data structure is correct in the sense that it indeed is an approximate set membership data structure. So essentially, it is just storing small signatures of the items.
So, I mean, the obvious thing would be, oh, that's going to be n over e storage instead of n log 1 over e storage.
Right. So now, if the data structure is completely succinct, meaning it's actually it doesn't store just it doesn't just put signatures in a dictionary in a naive way, but it's a succinct dictionary, so it reaches the informational lower bound, then in fact we get the right number here. And an efficient succinct dictionary came much, much later. So this dictionary has, at least in theory, it's also a bad data structure to implement in practice, by the way, but it reaches all these goals. So answering your question, it also has I think even O of 1. I'm not sure it even depends on epsilon query time. I should comment here that while this is a better construction from a theoretical point of view and arguably not a better construction from a practical point of view, it is a better construction from a practical point of view to do exactly as you suggested, just to take short signatures and put it in a properly designed dictionary, whether it's linear probing or cuckoo hashing. In that case, you will have to, you could do with signatures that are much smaller than this because the signatures are not compared n to n. You don't compare them to all the n, you're comparing them to a small subset, to a constant number of signatures on expectation, at least. And the reason, if we're talking about practicality, so Bloom filters, so Mikhail pointed out that you have to compute d hash functions, which is crazy in practice. Often the computation of the hash function is the most expensive thing. And then once you did that, you have d random accesses to the data structure where every random access is to take 1 bit. So it's really the least efficient data structure you can think of. And when you look at implementations, they never go all the way to log 1 over epsilon because at around 3 or 4 hash functions, they say it's too expensive anyway. So they deal with huge epsilons because of that. And if you just take a standard library, just a standard dictionary from Java or whatever, and store short signatures there, then you're better off already. And I have no clue why people are not doing it. So that's kind of a side remark to make Mikkel happy, because I know this upsets him. OK, and now an interesting lower bound that I have to say that I wish I would understand more is a separation between the static case and the dynamic case, where the dynamic case is a very minimal definition of dynamics. So I'll start with the upper bound. So Dietz-Filbinger and Pasch showed that if we get all the items in advance and we build something that is kind of similar in spirit to a perfect hash function with short signatures in terms of how it's built, then in fact we can reach more or less the lower bound. It's n log 1 over epsilon plus this is little o of n. So it's important here the low order term is little o of n. And in Stock 2010, Lovett and Porat showed that if the items show up one by one, so we don't get all the items in advance so that we can build this machinery to place them in a perfect hash with a perfect hash function, then the lower bound is in fact n log 1 over epsilon plus, say, omega over n and epsilon. So the exact function is not really important. So it's a separation between the static and the dynamic case. The separation is on the low order term, but it is still there. So it's kind of an interesting result. It's a little bit mysterious, I have to admit. OK, so what did we do? So when we're thinking about practical implementations, one of the main differences between the theory and practice is the assumption that n, the size of the set, is known in advance. All the upper bounds assume that. While in practice, items arrive one by one, and often we do not know that size. And provisioning for the largest n that we can think of up front leads to over-provisioning and waste of space as long as the set is small. And if we missed our prediction, then it's a waste of space. And if we are conservative, then we have to grow. We have to, at some point, throw away the data structure, build a new one. It's not clear how to do that with approximate set membership. So this is the problem that we came to tackle. And we actually kind of ran into some papers that suggested constructions to do that. I'm talking about papers in the in other communities. And it just, when we read them, it struck us as a very naive way to deal with something that is perhaps interesting from a theoretical point of view. So this is the problem that we set out to solve. And we have a matching lower bound and upper bound. That's always good because when you send a paper with a matching upper bound and lower bound, then even if the reviewers don't understand what you did, what the result, what the problem is, at least they understand that you've solved it. So that's always good. So so what is the setting? So let's say we have an n that is our upper bound. This is the maximum. We are willing to assume that we will not see more than n items. What we show is that there will be some m. And we can even show that this m would show up relatively late after root n items have arrived, but it doesn't really matter. There will be some m where the space would be m log 1 over epsilon, which is the lower bound for the static case, plus omega of m log log m. So if you think about the number of bits that we have to spend per item, previously it was log 1 over epsilon. Now it's log 1 over epsilon plus log log m. So this log log m is a superlinear bound. So it's a very modest one. But now it depends on the size of the set. So this is the stark difference between the dynamic case and the static case. That is, in fact, the heart of our result. I should say that I noticed, I'll just warn you right now, I noticed in the subsequent slides that I sometimes switch log log n with log log u. So if we assume that u is the polynomial in n, which is a common assumption, it's a reasonable assumption, then these are, in effect, the same number up to small additive terms. So just ignore that.
I'm not sure is this the same as saying that you're proving a lower bound of square root n of setting m equals square root n?
Setting m equal. I'm not sure I understood the question.
Is this equivalent to stating the lower bound of the space that is square root n times log 1 reps?
No, because here,
it's after inserting m items.
M items, yeah. So there will be, so what I want to say is that it's impossible to keep the upper bound that we know when n is given. It's impossible to have it continuously throughout the entire life of the data structure. At some point in the life of the data structure, if items arrive one by one, you have to over-provision. That's, you have to have a super linear number of bits, or super constant number of bits per item. And we have a matching upper bound with constant query time, so we can show that this is tight, actually. OK, is the result? OK, and the proof would be actually very similar to the encoding proof. It requires a little bit more maneuvers, but if you follow the simple encoding proof for the static case, then this is a breeze. So I hope this will not just confuse more, but the sanity check is all right. So what do we do with dictionaries? With dictionaries, there is the rehash. Whenever a dictionary reaches its capacity, we just put everything back in. We just build a new dictionary, which is larger, and move all the items there. So what happens if we do it here? Well, of course, we can do it. It just means that we need to over-provision space at the beginning, right? So yeah.
Sorry, just a question about the previous slide. So I guess the thing you can hope to prove here is that you can hope to prove a lower bound of this bottom thing without any restrictions on n.
On n?
On m.
Without any restrictions on m. So in practice, there are no restrictions on m.
Well, so it's possible to prove this line with the spaces at least this equation with no restriction with n. Could be possible.
Yes. The restriction on m is kind of super flush. N could be very large. N could be the entire universe to some extent.
Can't we imagine that n grows one by one, so n will actually take all possible values?
Yes.
So
Yes.
But
yeah.
n is very large, you're not proving anything, right? Because you're saying only if m items are inserted does your lower bound apply. So, like what I want to prove is that no matter how many items are applied or inserted, there's a lower bound. You're saying only if m is at least square root n.
So this is actually strengthens the lower bound. So.
But you're restricting the setup to saying that m items have been inserted, at least square root n items.
You're saying that there exists an m, that at some point as you do your insertions, there will be a point at which you screw in the sense of the large space.
But it only applies if,
Yes.
if m is bigger than square root n.
No.
So no. Also when so it's a stronger thing, right? It happens late. It doesn't happen early. It just strengthens the lower bound.
It wouldn't be very interesting.
So in retrospect, all right, let me rephrase it. In retrospect, after everything is done, you realize that you've inserted n items. All right, this is kind of ex ante.
Oh, n means that's the total.
N is the total, and now you look at the life of the data structure. There must have been a point, and this point is not even very early. It's after root n were inserted, in which the number of bits per item was large compared to the number of items that were actually in the data structure. Okay, so let's start working for the lower bound. It's a proof sketch. I'm cheating in a few places, not in many. Maybe you'll catch me, maybe you won't. It doesn't matter if you don't. So what we do is we partition the items to epochs. of length 2 to the I. So the first epoch is 1, second epoch is 2, 4, and so on. And we denote by SI the prefix of the first I epochs. Okay, so SI is not the ith epoch, it's the epoch of the first I epochs. It's the prefix of the first I epochs. And DI would be the data structure after each epoch. So now, here comes the crucial definition. For a prefix SI, we define a set A of SI. And an item X is in that set if there is any conceivable history of insertions that X belongs to that history, and it would result with that exact data structure DI. So if we can list a list of insertions that X belongs to, and at the end of that insertions we get the data structure DI, then we say that X belongs to this set. So clearly, this set is part of the yes set, because if X satisfies this condition, then we cannot know whether it, then it could have been inserted. It could be that the yes insert is actually bigger than that. We do not know how the data structure works. It's a lower bound. And it could be that this set is very hard to compute. Again, I am not claiming anything about the computability of the encoding. Okay, but when the answer set is defined in such a way, then we know that A of SI is contained in A of SI plus 1. And why is that? Because if an item belongs here, then we could play the history which manifested, which is the certificate for this item, up until the end of this epoch, and then insert the next epoch and get the next data structure. So we have this containment. Okay, this is in fact, the most important definition in this proof. So here I just repeated what I just said. And the last thing to note, if S is at the end the total number of, S is the full set, the full n items that I inserted at the end, then for the same reason that we had previously, this size is bounded by epsilon u.
So why is that? Because in principle, with this version of yes, you would have had elements that you would normally have said were temporary in the sets. Right? I mean, the way you define if somebody was...
No, it's a containment.
The set's only growing.
The set is only growing, and A of S is a subset of the yes instance. So A of S is at most epsilon u in size.
Can you do the last slide one more time? Sorry.
Yes. So we have containment, and we have that every set is a subset of the yes instance. So the final set is of size at most epsilon u. Okay, and now by an averaging argument, we know that there are two consecutive such sets that their difference is not too big, because we have a total of log n. So there were two sets that their difference is at most epsilon u divided by log n. So what we will do is now do the exact thing that we did previously, and we will try to encode one of the epochs, in fact the ith epoch, relative to this set. Because we know that the ith epoch is, well, it's contained in ASI, and all of it other than an epsilon fraction would be contained in this set. So let's ignore that. Let's assume that it's all contained in this set and ignore that epsilon fraction. So now what we have to do is to just write down both the data structures for the two times before the epoch and after the epoch. And then from these data sets, we can compute. It is computable to compute these two sets, ASI and ASI plus 1. And then encode the epoch, which is of this size, relative to the set that we just defined.
So BI is the data structure size of DI? Or what?
Yes, yes, yes. Exactly. So if we have the two data structures, we can compute this set and this set. and therefore we can compute this encoding. And
encoding of this is their set difference?
yes, yes. So we know this set and this set, so we know their set difference. So let's assume that the ith epoch is contained exactly in this set. In practice, most of it, only a 1 minus epsilon fraction of it is contained there, but let's ignore that. So this is the encoding of the ith epoch relative to this set. And we know that this whole thing has to be at least the size of that ith epoch. And this, so here should be m. It doesn't matter. This gives us the lower bound.
This is, you just have BI, you either have BI or BI minus 1. I'm sort of confused.
Right, so this is a lower bound on the average of these two, yeah. And it's a slightly weaker lower bound than I showed at theorem, because here I have a constant also in front of the log 1 over epsilon, and with a little bit of work, you can make this constant 1 and just play around with the constant here. I'm not showing that, but this is the idea, and it shows I think the power of just encoding-based algorithms, that sometimes you need to work a little bit hard and maybe define sets that are not easily computable, and then just the encoding gives you a very clean space lower bound. So how much time do I have?
15 minutes.
15 minutes. All right. So it's I'll spend probably the next 10 max describing the upper bounds. So I'll give credit to the paper where I saw this problem presented, in a different context. And what they did there is they did the natural thing. They just kept log n different data structures in parallel. So building a new one when everyone is being filled up. And you have to search all of them when an item shows up. So the ith data structure will store 2 to the I items. So we have log n. And it would have a false positive rate of epsilon I. And since we have to search all of them, then the summation of epsilon I has to be our false positive rate that we shoot for, which is epsilon. And in that paper, they suggested to have epsilon I be epsilon divided by something exponential in I, which leads to a n log n space. So it's suboptimal in space. And logarithmic query time, because you have to query all of these data structures. So of course, the first observation, the very quick observation, is that if you have the epsilon I shrink much slower, epsilon divided by I squared, say, times some normalization factor, some scaling factor, then you will get the optimal space. So the fact that just in terms of space, that's the right answer, the lower bound is the right answer, is very easy. But notice that there is a logarithmic query time. So the natural question is perhaps we do have a space query time trade-off here. Yeah.
So the way it works, right, if one of them fills up, you query all the elements, you query all the universe, that's how we figure out what to put in the next one.
So you need to have a counter how many items you've put in each one, and when you've reached 2 to the I, you build a new one. No, you don't. You just start inserting from that point on.
You have to look at each of the old ones to find.
Also, you don't merge.
You do not merge. You cannot merge. So the whole thing is that you cannot merge because, yes. Yes. Yeah, I'm sorry. Yeah. So you do not merge. You just build a new one and you search all of them. So this kind of very naive way shows you that the space bound that we have, and I don't do here the calculations, right? But it's, just write it down and it gives the right number. So this shows you that the space lower bound, as a space lower bound, is correct. And of course, the natural question is whether, is there a different time-space trade-off here? So is the logarithmic query time really necessary? And the answer is no. with a little bit of work, we can show a data structure with constant query time and the same space. So I can sketch the idea of how to do that. As before, we partition the assertions to epochs. So we will have ni as the size of that of the current epoch, and that would be our n. So I have here n, but think of n as the n for the current epoch. And remember that we had the solution of just using, say, a universal hash function and storing signatures of length log n over epsilon, right? That was kind of in the first slide. So let's do that. But the trick here now is that we have a fingerprint of size log n over epsilon, or log ni, because that's the size of the current epoch. But we will, in fact, cheat a little bit, and we will have larger signatures. And larger signatures, we will have log log, again, log log u, log log n, it's all the same number. We'll have log log n bits more on this signature here. And I will explain why we make, why we are throwing these extra bits. But the key thing is that for now, let's say we are in this epoch. We have not moved to the next epoch yet because no new items have arrived. We have the complete standard dictionary-based data structure that we described previously. So given a query, we just search for this signature. OK? So now why did we have here the extra space? So within an epoch, essentially, the dictionary is similar. But what happens when an epoch ends? So when an epoch ends, we suddenly now have too many items. So now this is the place where we use these spare bits. And what we could do is just move one spare bit from the spare part to the actual signature and get a longer signature. And this thing will, again, for the exact same reason, work until we ran out of these spare bits. So the only question that happens is what to do when we ran out of these spare bits. So I'll just briefly repeat. This is our signature in the current epoch. Now when we move to the next epoch, we need a signature which is one bit longer. So we just take a bit from the pre-computed bits. So we rebuild the dictionary with larger signatures. And the only problem is what happens when we run out of these spare bits. And I'll explain that soon. But is this part at least clear? Paul?
I'm confused how these are stored and how you access them.
So that's bookkeeping. It's a dictionary, but that's bookkeeping for the purpose here. So we store based only on these signatures. Think of it as a key-value store if you want, that this is the key and this is the value. OK? And now when the epoch moves, we actually need to have one bit more to the keys. So we can grab it.
Build a new table?
Yeah, we build a new dictionary. We rebuild it.
Oh, I see. So you're actually going to,
yeah.
at this point?
At this point, I have to rebuild it.
OK. So you're not, that's not?
Yes.
This is advertised. This is not a
Yeah. Yes, for the insertion time, yes. For the query time, it is still oval. So this is completely standard. The only problem here is that we have very few bits here. We have here log log u bits. And the only question is what happens when we ran out of bits here. So the key observation is when we run out of bits, we can be conservative, and we just add both a 0 and a 1 and insert both. So we have both signatures there. So note we inserted too many elements. We may increase our space and our false positive rate, but we'll take care of that. For now, just in terms of correctness, clearly that is fine. We're being conservative, and the signature is still there. No matter what the real signature is of the real item, it would be either with a 0 or with a 1 at the end. So now let's compute how many superfloss, how many unnecessary items have we inserted. And an item is inserted in epoch j. It will create, well, we have log n epochs minus log log u, which is the extra bits that we had, minus j, which is the epoch in which it was inserted. So this is the number of new items that were caused, the number of new insertions that were caused for an item in epoch j. And now if we multiply it by the size of the epoch and by the number of the epochs, we get that in total we have O of n. So we increased the total number by a constant fraction, so everything is, so the FPR is reduced by a constant fraction and everything is fine. So I'm not sure this is a good idea in practice, but yeah. 5 minutes, okay. So I'm not sure I even want to take these 5 minutes. There are these extensions and standard tricks that you can do. So when you rebuild, then in fact what you have to store both of them simultaneously, and we're claiming a lower bound on space. So we are doubling the space. So can we avoid that? Well, yes, you can avoid it by kind of bucketing and sharding and standard techniques that are not interesting, honestly. And I should say that while supporting deletions is not very sensible, it is sometimes sensible, and in these data structures. And when you have dictionary-based approximate set memberships, then you can support deletions. You can delete. There is no problem. It's just deleting like a dictionary deletion. You just have to make sure that the item that you deleted was indeed inserted, because otherwise you create false negatives. So when you think about the situations in which these data structures are used in practice, then this is often the case. So if you think of a web proxy, then at some point the web proxy decides that it does not want to keep a certain page. So it could go to the filter up front and remove that page. So in that case, the user, which is the user of the data structure, which is the web proxy, knows that this item was indeed in the data structure because it inserted it previously. Yeah.
Problem with two actual items having the same.
Yes. So collisions is right. So if the dictionary allows for multisets, then you can then you can remove. If the dictionary does not allow for multisets, then you need to have the extra assumption that you do not have collisions. Yes. These are the usual considerations, but it is worth noting that the standard Bloom filter doesn't even support that, so which is a very basic requirement in the places where these data structures are applied. Yeah, so this is just what we said, so I'll ignore that. So this is, I think, a fairly close problem. So there are not a lot of open problems left directly in this kind of niche of a problem. I am curious. I mean, I haven't, and as far as I'm concerned, no one has really drilled down what is the indeed best and fastest way to actually implement these things. And while we can tighten up the constant in front of the log 1 over epsilon, we're still kind of loose on the constant in front of the log n at the end. So there is some work there still to be done. I think that's it. Thank you.